Hello, class. So on this video, we'll finish example 4 in chapter 4, and it's the last thing we have to do. So we're working on this differential equation, solving it using the method of variation of parameters. We couldn't use the method of undetermined coefficients because tangent of x is not sine, cosine, exponential, or polynomial, or a combination of those without dividing. Right? So tangent is sine over cosine, but we don't want to divide. Right, so we can't use the method of undetermined coefficients, so we have to use variation of parameters. Right, so first, as usual, we find the complementary solution. Right, so find the characteristic polynomial, set it equal to 0. You have your complementary solution. Second, right, we have our form for a particular solution. It's going to be u1 times y1 plus u2 times y2 plus u3 times y3, where y1 and y2 and y3 come from the complementary solution. Right, they're the three linearly independent solutions. And then we find an interval in which each of these, well, not each of these, but each of the p sub i's, remember the p sub i's were the coefficient functions of the differential equation after you divided by anything that was multiplying y triple prime, or the highest order derivative, which in this case is y triple prime. In this case, whatever was multiplying y triple prime is 1, so we don't have to divide by anything. So we only have one p sub I, right? It's the one multiplying y prime, which is 1. So we have p sub 1 equals 1, and then g of x equals tangent of x. So we first find an interval in which those two are continuous and in which the complementary solution exists. So we found one such interval to be negative pi over 2 over pi over 2. Right? So we did all that work before. I'm just summarizing. Then, by the theorem, or not theorem, but the method that I gave you, we have an equation for each of the u sub I primes. And then, just a reminder, in the previous video, I wrote this backwards, right? I wrote w divided by w sub k, right? Where it is correct as it is here, w sub k divided by w. So it is correct as I had it above. I just, for some reason, I spaced out and wrote it backwards here. Right? But anyways, we have to find each of these determinants, right? So we went over all that work a couple of videos ago. We found w, which is just a regular Wronskian of the y sub i's. We've set up that determinant matrix. Then we set up y1, y2, and w1, w2, and w3. Right? And these are basically the same Wronskian as w, but you replace the ith row. So w1, you replace the first row, column, sorry. w2, you replace the second column. W3, you replace the third column. Right? What do you replace each of those columns by? You replace it by a column involving all zeros and last entry being tangent of x. So for example, for W1, we replace the column 1, 0, 0 with a column 0, 0 tangent. W2, we replace the column cosine, negative sine, negative cosine with 0, 0 tangent. Right? W sub 3, we replace the third column, which is sine, cosine, negative sine, again with 0, 0 tangent. Once you have all of these written down, and you can write these on paper, right, then it's now time to find each u sub I prime, right, which by definition is w sub I divided by w. Now we went into Mathematica and calculated each of these determinants. Right, so we went over a video of how to do that. It's a quick video, but still enough to see how to do it. And let me write the results that we found. Right. First of all, we found that w, just the Wronskian of y1, y2, and y3, was sine squared plus cosine squared, right, which is equal to 1. Right. W1 was sine x times cosine x plus sine x times tangent. Right. And then W2 and W3 were 0. So let's go ahead and find each of these u sub i's, right, by integrating each of these ratios. So let's start with the hard one. W1 prime is going to be W1 over W. In this case, W1 is sine x cosine x plus sine x tangent x. Right? Since W is just 1, this is what we get. Right? So we integrate both sides. So u1 would be equal to, after moving the constant, right? So sine x cosine x plus sine x tangent x Oh, I don't know why I wrote a square. Sorry. It's tangent x dx, and then you're going to get a constant of integration from here. So think of us combining the one on the right-hand side with the one on the right-hand side later. And then we make it equal to 0. Because again, we only need one such constant. Sorry, we only need one solution u sub 1. We don't need infinitely many, which we do get because we had infinitely arbitrary constants. So we just choose the easiest one, right, where the constant is 0. So this one is a little bit tricky to integrate. I could leave it as an exercise, but I think it would take you a little bit of time, and I don't really want you to spend time on something like this. You could integrate it in Mathematica, right? If you go to Mathematica and to wire courses, to the modules, then go to Mathematica, and then Mathematica help, I show you how to integrate. But here, you can integrate this just by noticing that we can rewrite this as sine x cosine squared x over cosine plus sine x cubed over cosine. Right, so all I did was get a common denominator. Rewrote tangent as sine over cosine, got a common denominator. Right. Now, if we factor out a sine on the numerator, leave the denominator as is, we get sine squared plus cosine squared left over. We know that's equal to 1, so this integral was actually just a really disguised way of writing the integral of sine over cosine. Like this we can easily find doing a u substitution, so a little bit of calc 2. So u equals, cosine x, du equals negative sine dx, right? So this means that negative du equals sine x dx. And so then replacing this in the integral, we get the integral. So the negative out front that we get from the negative du, 1 over u. What is this equal to? Well, negative natural log absolute value of u, right, plus a constant, which equals negative natural log of cosine x, right, absolute value of that, plus a constant. Right. We're going to let that constant be equal to 0, as we mentioned. So u1 then is just the negative natural log of the absolute value of cosine x, and then set the c equal to 0. Okay. Now that's u1. Let's do the other ones, which are easy. Right. u2 prime is w2 over w, which is 0 over 1. Remember, w2 was 0, which is 0. Integrate both sides. And I get integral of 0 is a constant plus c, which is just a constant. Now remember, the constant is arbitrary. Right? We only want one such u sub 2. We only need one of them. So again, you set c equal to 0. So set c equals 0, which implies u2 equals 0. Right? Similarly, do the same work for u prime. U sub 3 prime equals w3 over w, which is 0 over 1, which is 0. Do the same choice, integrate, same choice of constant, you get u3 equals 0. Okay. So what's the general solution? General solution is, well, first let's write what y sub p is. Y sub p is u1 times y1. u1 was the negative natural log of cosine x times y1, which was, I don't remember, it's written up there, plus 0 y2 plus 0 y3. Because u2 and y3, we chose them to be 0. So our particular solution is negative natural log of cosine x. And then let me look up what y1 was actually, just to put it in here. I think y1 was just 1, right? Yep. Yeah, so y1 is 1. So then this is just equal to y1, sorry. which is just equal to negative natural log of absolute value of cosine x. Now, we can simplify this even more. Right? Why? It'd be nice to get rid of that absolute value, right? Because if not, you have to consider plus or minus. Right? Well, how can we do that? Well, remember that the interval we're working with, right, we did this a long time ago, was negative pi over 2 to pi over 2. Right? That's the interval in which this is a particular solution and in which we're going to define the general solution. What do we know about cosine x in that interval? Well, in that interval, you can bring out your unit circle if you don't remember, cosine x is positive, which means that this simplifies to the negative natural log of just cosine x. Of course, on negative pi over 2 to pi over 2. Right. So, what's the general solution? On negative pi over 2 to pi over 2 is y of x equals y sub c plus y sub p, which equals, so let's go back and see what the complementary solution was. So 1 cosine sine, so c1 plus c2 cosine x plus c3 sine x, that's the complementary solution, plus the particular solution. So there's a minus in front, so let's make it a minus. And that's the general solution on negative pi over 2 to pi over 2. Right? So a lot of work, but if you write each step down as we did in this example, right? You first do the complementary solution, then find an interval in which each of the coefficient functions are continuous and g of x is continuous, and that is shared with the complementary solution. Right? So that's where we found I, being negative pi over 2 or pi over 2. Then you can just write each of the Wronskians that you have to find, use Mathematica to find them, rewrite your u sub I primes, integrate, and then write your y sub p. Once you have y sub p, you have y sub c as well, you have the general solution. Okay. And this is the end of chapter 4. As you see, everything generalized from second order differential equations, as long as they're linear, to higher order differential equations. Or we could have done this with a nth order differential equation where n is 5, 6, 7, 4, 3, 10, 1,000, 10,000, etc. Everything generalizes nicely, again, because of linearity. That's the important thing. Not so much the order, but the linearity. Okay. So, again, as I mentioned, this is the end of chapter 4. In the next video, we're going to start on chapter 6, I believe.